Certification of composite components or composite structures that require high reliability is generally complex and expensive. In the aerospace manufacturing sector, safety is especially paramount. So certification requires expensive programs of testing before a new structure can enter production. The testing methodology there is commonly referred to as a test pyramid, where at the lowest levels, material coupons are tested, followed by increasingly more complex building blocks. Finally, at the top, the entire structure is tested. The fundamental issue during testing and certification is the inherent uncertainty in material properties, in bond properties, in the loads, in the geometry, and so on. So we have a lot of sources of uncertainty. This is especially true in composites, where the material behavior is strongly influenced by the material microstructure. And even with precise process control, a certain variability in material response must always be expected. Now, we can already reduce experimental effort using simulators or digital twin approaches, but we need confidence in those models. And the question, therefore, is how can we certify structures facing these uncertainties while reducing experimental effort and therefore cost? And I'm pitching an artificial intelligence assistant uncertainty quantification method to capture uncertainty on the material level, propagate the uncertainty through building blocks, and quantify the impact of the uncertainty on the structural response. So basically following the test pyramid. And the methodology I'm pitching can be broken down into three solution strategies. So the first strategy is quantification of uncertainty on the material level using AI. And this is actually part of the research I've been working on. And we've shown the feasibility of this approach for simple application. So basically neural networks estimate the stochastic behavior of a material based on surface strain distributions. And this enables fast estimation of uncertainty on the material level with greatly reduced experimental effort. The second strategy is using AI-assisted adaptive surrogation to reduce computational expense during uncertainty propagation. Now, generally for uncertainty quantification, we need a large number of stochastic model evaluations. But for example, if we have a complex progressive damage simulation, which can take hours or even days, this might be infeasible. So instead, we can use multiple surrogate models with increasing fidelity. The low fidelity models provide fast results that can be refined by additional evaluations of higher fidelity models. And AI can assist with choosing the required fidelity and tracking the confidence based on design domain knowledge. And finally, the third strategy is to use sample efficient methodologies. Machine learning based sampling methods can efficiently sample the design space while keeping the required number of model evaluations low. So research exists for all those three methods individually, and all methods have generally been shown to be feasible for simple problems. I believe that by combining these three approaches in structure development and certification, we can greatly reduce the required experimental effort and therefore lower development costs while increasing confidence in our results. So thank you very much for your attention.